Today I'm going to present this PDF file where you can already see that the discussion on t-test is mentioned. Regarding t-test, I once discussed with you the technicalities were discussed and how to find the p-values, etc. I explained it in terms of uh, a theoretical discussion, but problems were not actually done properly. So in this particular class, I'm going to explicitly explain a problem on the application of t-test for testing the validity or the hypothesis about population mean that has been made. To remind you, t-test is a kind of test which is often used in small samples, and t-test is also a kind of test which behaves like normal curve, normal variate. So whenever you will do the problems related to t-test statistic, you will find that we'll be explaining things in terms of normal curves. So the t distribution is a kind of normal distribution which satisfies most of the properties of the normal curve, but the advantage of t distribution is that it can also be used in the problems related to small samples. Previously, people thought that if the sample is not large, then we cannot use use any statistical methods to the sample. To use statistical methods to the sample size has to be large enough. But later, this particular notion was broken by the introduction of t distribution by the statistician Gosset, and after that, this t distribution has got its tremendous amount of applications in various other fields. Whenever I talk about the sample size being 30, whenever I talk about the sample size being small, I consider the sample size being less than 30. And if the sample size is greater than or equal to 30, we call it as large sample. I mentioned before that equality symbol can fluctuate between our it can vary from author to author. Some author consider the equality sign with the less than symbol, and some authors consider the equality sign with the greater than symbol. So it doesn't matter at all. If you say that the sample size is less than or equal to 30, you want to consider this to be the small sample, no problem with that. But it has to be less than 30. That is the most important part. This type of problem, which I already explained to you earlier, but today I'm again going to discuss on this particular issue from the viewpoint of a problem, and I'm going to explain explicitly how to calculate the p-value. So to begin with, we assume something for the population mean mu, and suppose the value that we have assumed or guessed for the population mean is mu naught. If we consider the two-tailed test, this two-tailed test is considered when we cannot say anything about the upper tail or lower tail explicitly. Then in that case, someone has written. Just a minute. So if we do not consider the upper tail or lower tail, if we do not have any idea about the upper tail and lower tail, then we are not sure enough which particular portion we need to consider. Then only we use both the tails. Both the sides are open. So we consider this to be a two-tailed test. First of all, I'm going to explain the calculation of t distribution corresponding to a two-tailed test. Generally, in these situations, we used to use Z statistic, whose formula is very similar to the formula which we'll be using over here. If I want to recall you about the Z formula, the formula for testing goes like this. It is x bar minus mu naught by sigma by root over n. But the problem here is that we do not know anything about the population standard deviation and hence the population variance. So this sigma needs to be estimated by some sample observations, and that sample observation is calculated. This observation, I mean this sigma, the population standard deviation, is actually calculated with the help of sample observations, and the formula that we use is given by this that I have mentioned over here. This formula is already mentioned over here. The main important factor in this particular formula is that whenever we want to calculate this type of deviations, we call it standard deviation, no problem with that. We always divide the sum of the squares by sample size minus 1. This is the main part, because it can easily be shown that this type of sample statistic correctly estimates the population parameter sigma. If we divide this sample statistic by n, then it will not correctly estimate the population standard deviation. There is a theory. The proof is also, you can find the proof in John Freund's book also. Anyways, I'm not going to get into the details. So this particular part that I'm actually moving my cursor, this particular part was not known to the statisticians in earlier years. They thought, then they knew nothing about this portion. Probably we are not feeling it right now because we have got it ready-made. But when it was not there, suppose some way when it is not available, then we have to think of certain ways to find out the solution. In earlier years, this way was not known to anyone, any statisticians, and they thought if sigma is not known, then we are done. We cannot do it. We cannot do the hypothesis testing. If we want to do the hypothesis testing, collect as many sample points as you can. Now, as you have got our theory, so we can replace this capital Z by small t. We name it T with respect to its inventor Gosset, and he used to write his paper under the pen name student. As I've already told you, the formula looks very similar. The only difference is in place of sigma, we are going to put capital S. And since capital S, to calculate capital S, we divide by n minus 1. So we often say this type of statistic T follows T distribution with n minus 1 degrees of freedom. Degrees of freedom are the number of independent variables that are required to test the system or to calculate something on the basis of the observations. Okay, since capital S, inside the capital S, n minus 1 is hidden, so the degree of freedom is n minus 1. But we are dividing this quantity by root over n. Remember, here n minus 1 will not come. Now let us proceed. Now, as I told you that this T distribution just behaves like the normal distribution. So we have got the normal curve like this, and I have drawn two vertical lines over here. This picture I have not copied from anywhere. I have drawn it in Microsoft Paint. So you see that the drawing, you can understand very well that it is a kind of hand drawing. These two vertical lines which I have put over here, these vertical lines are the value of the T statistic. When we substitute the values of these individual terms, we get some value at n minus 1 degrees of freedom. Why? Because capital S is calculated by dividing the sum of squares by n minus 1. If we consider the negative of this value on the left hand side and positive of the value on the right hand side, so we can represent it by minus Tn minus 1 and plus Tn minus 1. But if I show you this particular, this particular chart, which I already sent you earlier, you can very well see that these probabilities have been calculated on the basis of the right hand side only. as you can see. Here, they have drawn the normal curve. And since it is a normal curve, it is a standard normal curve kind of thing. So the mean value here is 0. And the entire probability is calculated on the basis of the right tail. So they have shaded this portion and they pre-decided some level of significance. Level of significance is the probability of rejecting the null hypothesis when it is true. So they consider this level of significance alpha, and for different levels of significances and for different degrees of freedom, they calculated certain probabilities. So they have written Tn minus alpha. So it is a kind of probability chart which is given for one-sided test. But here in this particular case, if I consider a level of significance at certain value, say alpha, and since my test is two-tailed, so we'll divide alpha into two halves. One portion for this and another portion is for that. Okay. So this area of this particular portion on the lower end will be having the probability alpha by 2, and this area on the upper end will be having the probability alpha by 2, so that the total probability is alpha. Total level of significance is alpha, and hence this point has been mentioned here. I have mentioned this point. I have denoted this point by Tn minus 1 alpha by 2, and this as minus Tn minus 1 alpha by 2, since it is a two-tailed test. And the criteria is that you are going to reject your null hypothesis when modulus of this T is greater than or equal to the tabulated value of T at these degrees of freedom and at the level of significance alpha. Otherwise, we are not going to reject the null hypothesis. Now, probably you know from your real analytic theory that whenever we write mod x greater than mod a, this actually means x is less than minus a or x is greater than plus a. Okay, so whenever I write that reject your h naught, so when mod of t is greater than this value, that means either the value is falling inside this region or the value is falling inside that region on the right hand side. So with respect to this real analytical theory, this criteria has been maintained. Okay. So these are the this is the criteria by which the conclusions will be drawn. Let us now proceed. Now here is the chart, the complete chart by which you can do the thing. That will, this complete chart, I have pasted it from, I have taken the screenshot of from the page of a book and I have pasted it over here. So very well you can understand that it is not a kind of it is not my typing, it is something different. So I pasted this picture for your clarification. Here it is written the one sample t test, because I have actually considered a single population. From single population, I have drawn a single sample, and therefore it is called one sample t test. And null hypothesis has been designed in the following manner. Formula you have already got. This formula is called test statistic. Any measurement, any sample measurement is called statistic. And the alternative hypothesis can be of several types. If your alternative hypothesis is two-sided, we will try to draw our conclusion on the basis of these values. If it is one-sided upper tail, we will try to bring the conclusion from this. If it is one-sided lower tail, we will try to bring the conclusion on the basis of that. And this particular picture, this particular chart has been is corresponding with this particular figures. As you can see, the first figure on this first figure A corresponds to the case 1 of the alternative hypothesis. Figure 2 corresponds to the case figure 2 corresponds to the case 2 of the alternative hypothesis, and figure 3 is case 3 of the alternative hypothesis. To calculate the p-value for a t-test, the meaning of the p-value will always remain from test to test. P-value is the smallest level of significance at which the null hypothesis would be rejected. That is, it is the tail area beyond the value of the t-statistic t-naught for a one-sided test, and or twice this area for a two-sided test. I shall explain this point of p-value with respect to on the basis of a problem that I have solved over here. Now we have a problem in front of us. it is given that the specifications for a certain kind of ribbon call for a mean breaking strength of 185 pounds. So obviously this mean breaking strength, which is mentioned over here, this is the mean breaking strength of the population, which is 185. So automatically you can write, immediately you can write that our null hypothesis is the population mean mu, which is actually denoting the mean breaking strength, which is 185. We want to test it. If 5 pieces randomly selected, instantly you can say that since I'm selecting only 5 items, so definitely it is less than 30. So it is a small sample. Okay, so it is a kind of small sample test. If 5 pieces randomly selected from different roles have breaking strengths, so 5 values are given. So this 5 value will contribute in calculating the sample mean strength, sample mean breaking strength. So these are my values, sample points. Test the null hypothesis that this is true against mu is less than 185. Now it's specifically mentioned that you have to consider the lower end to one-tail test. So we have mentioned it here in alternative hypothesis, mu less than 185. And in the question it is mentioned, consider your level of significance to be 5%. First of all, from this, by looking at this particular problem, immediately understand that this is a problem of one sample t-test. This and nothing is mentioned about the variance of the population or standard deviation of the population. So obviously from this particular question, we can say that the variance is not known to us. So we have categorized the problem to be falling into the category of one sample t-test. So very well, we can use the formula over there. First of all, our job is to, and we know what the formula is. So first of all, our job is to calculate this sum of the squares of the deviations. So we have prepared this chart. Xi is having these values from which you can easily calculate the mean. Xi minus X bar is the deviations of the means from individual points. And sum of the squares of the squares of the deviations have been calculated. And from this particular row, the sum of the squares of the deviations for these 5 samples have been calculated. This has been calculated because we need to calculate capital S, which is going to estimate the population standard deviation. But at the time of division, we have to keep in mind that we need to divide this quantity 270.212 by sample size minus 1. And our sample size is 5. So it would be divided by 4, which is 8.2191. Okay, so we got our capital S. Already we have known our formula, which is X bar minus mu naught by capital S by root n. Substituted all the values over here. The value came out to be negative, which is approximately minus 0.51. And according to the rule that I set earlier, this calculated value will be compared with the tabulated value. But remember, it's a one-sided test, but level of significance is actually considered to be alpha. Alpha is 0.05. You will go to the statistical chart and you will identify the level of significance over here, 0.05. And this level of significance will correspond to the degree of freedom 5 minus 1, which is 4. So the tabulated value will be 2.132. Okay. Although I have written here alpha by 2, just to make you understand that one part of the problem, I mean, this is one tail test. So since the level of significance is alpha, so both the parts, another half of alpha, another part of alpha by alpha is on the right hand side is present. We are not considering it because we do not know anything about, nothing is mentioned about the upper tail. What is going to happen if mu is not less than 185? Is it greater than 1? I cannot say whether in any case, for any sample, it is going to be ever larger than 185. That particular part is not known, or whether it is after all acceptable or not. But since alpha is the level of significance, do not think that since we have calculated 0.05 by 2, we shouldn't consider the level of significance at 0.025. It is mentioned at 5% level of significance. That means 5% level of significance. That value has to be considered, which is 2.13. And we know that calculated value, if it's less than the tabulated value, null hypothesis is not rejected, or we fail to reject the null hypothesis. Next comes the part which is very important, is called the p-value part. Now, if suppose we want to test the p-value of the current problem, what will we do? So what I have done over here, I have mentioned all the level of significances. I have copied it from the chart, and all the critical values I have copied. These critical values, just look at these critical values: 0.271, 0.741, 1.533. These critical values correspond to this particular row, which is for n-1 degrees of freedom. So this has been pasted over there. Let us now come to the calculation of p-value. And I have tried in this particular note to explain explicitly how to calculate the p-value on the basis of the given problem. So just pay attention. In the subsequent problems, I have not explained about anything about p-values. You are going to do it by yourself. But here I'm going to explain it in explicit manner. In no book you are going to find this explicit representation or explicit calculations of p-value. In books, what they do is that they run some programs, statistical software like SPSS or R or Python or whatever, and or Minitab, and they just directly give the value. So this is the value which we have obtained, but they do not explain it. I have seen several statistics books. So this is here goes the explanation to you. So we know that p-value is a kind of probability, is a level of significance at its lowest value. Now, as per the definition of the level of significance, we know it is a probability of rejecting null hypothesis when null hypothesis is true. So I have written here in short, probability of reject null hypothesis given that H0 is considered. Or it is similar to probability of accepting alternative hypothesis given that null hypothesis is true. Alternative hypothesis is, you remember, it is one-sided here. The alternative hypothesis, just keep this in mind, it is mu less than 185. So it is one-sided. Just remember this point, because I'm going to use this particular notion in calculating the p-value. Now carefully understand what is going to happen over here. For your sake, I'm going to draw a very simple diagram, very simple diagram like this. And suppose this point is 185, which I'm about to test. Now, what is happening? The sample mean can take different values, and here, as the test is one-tailed, the null hypothesis will be rejected. Okay, so we have, on the basis of the sample mean breaking strength is 183.14. We have already used it. So the sample mean breaking strength, let me write it over here, because otherwise every time I have to scroll up. So X bar is equal to 183.14, which is the sample mean breaking strength. I use this symbol, capital X bar, sample mean breaking strength. Now this value that you are getting, from this calculation is based upon the samples that you have chosen. Now, if another person goes and collects the sample, his sample mean will not be exactly equal to 183.14. Any person, any layman can say it. His sample mean will vary slightly or hugely from your value. It depends upon the sample observations. Or it can fluctuate around 183.14, or it will fluctuate around 185. To get exactly the hypothetical value as your sample value, that is this probability is very low, very low. To calculate that null hypothesis is true, but we are going to reject the null hypothesis, what will happen? If you can recall my previous calculations of alpha, we are going to, on the basis of the sample observations, we are going to reject the null hypothesis if my sample mean breaking strength is less than or equal to 183.14. Okay, but if X bar, suppose so I'm considering this, according to my calculation, the mean breaking strength, the sample observation, sample mean breaking strength is lying somewhere here at this point. So I am considering this point to be 183.14. Okay. Now, if X bar is greater than 183, three cases may arise. What are the cases? One case is that if this happens, that your sample mean breaking strength is greater than 183.14 for some other samples, other set of samples, other set of 5 observations, three things are going to happen. What? This implies that either your value is going to fall in this region, or it is exactly 185, which is very feeble, or it is going to exceed 185. So these three cases may happen if your value X bar is greater than 183.14. Now, if your value is exactly 185, suppose this case 2 is happening, that means in this particular case, null hypothesis, you cannot reject your null hypothesis because it is, your assumption is actually telling with your sample observation. And since the case is not upper tailed, nothing is mentioned about population mean being greater than 185, nothing can be said if the case 3 happens. Because after all, what, at the end of the day, you are actually estimating a population mean on the basis of the sample mean, X bar. So X bar exceeding 185, that means your population mean is actually exceeding 185, because X bar correctly estimate is the unbiased estimator of the population mean. We cannot say anything about this particular case. So this null hypothesis can be rejected in two cases. One case is that if your X bar is less than or equal to 183.14, if this is the case, when your null hypothesis is rejected, or if it falls within the limit 183. Okay, I'm writing here, it is a printing mistake, 183.15 I have written 183.14 to 185. If it is falling inside this region, then your null hypothesis is going to be rejected when the null hypothesis is indeed true. I am considering these two cases A and B separately. First of all, I am considering this case, X bar less than 183.14. Now, I am going to calculate alpha on the basis of this case A. Now, alpha is probability that sample mean is falling below 183.5. If it is falling below 183.5, point is, why am I rejecting it? I am rejecting because it is falling below 183.5, 183. Sorry, it is a printing mistake. Again and again, it has happened. Somehow, while calculating, my mind was playing. My mind, 183.5 was playing, and I kept on typing 183.5. Before posting it in Google Classroom, I'll make it 183.14, but it will not hamper my calculation, because the value that has been calculated over here, that is minus 0.51, exactly tallies with my value that I have obtained earlier. Now, remember, listen to me very carefully. What is happening over here? Why am I considering this particular portion to be a rejection area? It is because 183.14 is actually less than the 185. There is a difference between these two values. Now, if your X bar is further lesser than 183.14, that means it is further away from your hypothetical population mean. And this should not be. You are going away from your population mean. That means whatever you are preparing in your company, whatever product you are preparing, it is not meeting the specification. So there has to be some kind of bounds, because beyond that you cannot go. Okay, so I am considering this region. If X bar comes less than 183.14, I am considering this to be the rejection region. So considering the null hypothesis to be true, that means considering mu equals to 185, I am calculating this T statistic. So I'm standardizing the thing by subtracting 185 from both sides and divided by capital S by root over n. And you have already done the calculation, which is T less than or equal to minus 0.51. Now, if I draw the T statistic once again, then suppose this point is minus 0.51 and suppose this point is plus 0.51, and you know T statistic behaves like the normal curve. So T less than or equal to minus 0.51 is exactly similar to T probability that T greater than or equal to 0.51. Now let us come to the chart which is given to us in the book. Now in this chart, they considered the T distribution and they calculated several probabilities, but unfortunately the value 0.51 is not present directly over here. What values they have got? They have got 0.271, 0.741, like these values are there, isn't it? So what does this mean? I'm again showing you the area. The area is this one. This is the curve for which the probabilities have been calculated. Now, whenever they write that corresponding to this critical value 0.271, the tail area is 0.4, it means the following. It means that we have this curve of T curve or normal curve for small sample. This is 0, and suppose this point is 0.271, and this area is having the probability 0.4. Okay, 40% is the chance that you are going to fall into the rejection region. So this is the meaning of this particular chart. Now, and this is the region, the critical value is going to be exceeded by the values. The critical value here is 0.741. You know, critical value is the boundary between the acceptance region and the rejection region. So here this area is going to be the 25% of the total area. Now what is happening over here is that if I draw the diagram once again, suppose this point is 0.27, this point is say 0.741, and suppose my value is falling inside the region 0.271 and 0.74, which is 0.51. Now what have I got? What is the probability that this critical value, my critical value is 0.51. What is the probability that this critical value will exceed 0.51? 0.51 is falling inside the area given by this critical value, which the area is 40%. Now this, I am actually interested about this area, but you see this is not a normal curve and you cannot calculate this area, isn't it? These two areas are not same. No way you can calculate it. But since this equality sign is over there, you can at least say that we can at least call it as what is the probability that this critical value or this value 0.51 is falling inside this region. According to the normal chart, this according to this T distribution chart, this area is 0.40. So this is not exactly but approximately equal to 0.40 from the chart above. Okay, and therefore it implies that this level of significance is the lowest level of significance at which this null hypothesis is going to be rejected. If you can consider any level of significance higher than that 0.40, then also you are going to reject your null hypothesis. But you see, 0.05 is the level of significance which is less than 0.40, and therefore at this level of significance the null hypothesis is accepted. So in the above calculation, we could accept the null hypothesis at the level of significance 0.05. So this observation that I have made over here is directly telling with the observation earlier obtained by the calculation which I did a few minutes ago. This is one part. What will happen for the case B? Then the case B, the same thing is going to happen. In case B, another area that I'm not considering, I'm not considering as acceptance region is this one. So X bar is actually can fall between these two. What will happen over here? So if I repeat the calculation, so I'm going to, if I standardize the variable this variable, or just a minute, I have activated the chat box. You put your attendance over there quickly. So if I calculate, standardize the variable X bar, and you are going to get this kind of probability. So T will fall between -0.51 to 0. And if I draw the normal curve once again, what will I find? I will find that this area is similar to this area. And from the chart above, and if you draw the figure once again, you will see that this particular area is also very similar to, it's actually approximately equal to 0.40. Since this equality sign is there, we can say that, yeah, T equal to 0.5 when it is falling in between 0.27 and 0.74. So it is falling in the rejection region, which is having the 40% probability. So here also it is approximately equal to 0.40. Actually, I shouldn't use the notation equality. I should use the notation approximately equal. So in both the cases, we are actually finding the p-value to be 0.40. So any level of significance which is greater than the p-value is the at those level of significance, we are going to reject our null hypothesis. Okay. So this is directly telling with my calculation. Now my less than 1 minute is remaining. So in the next session, I'm going to explain the paired sample t-test. I am stopping over here right now, and meanwhile we put the attendance for this first session. We are going to discuss again on the second session.